mishmash potpourri, if you will. Two topics. If you're good at identities, these will be fine. If you're not good at identities, these will make it worse. So here we go. What would you do?
Multiply.
Okay, now that is excellent. I was hoping you would say that. You would cross multiply because wouldn't that be great? It would be 1 minus cosine squared equals sine squared, and that's true, yeah? So is that what we should do? No. You just broke one of the rules of identities, which is you use both sides. You cannot do that. You can work one side, not both sides. Now, that said, you're on the right track. Because you're saying, gosh, wouldn't it be great, though, if I could multiply that by 1 minus cosine? So that's what you should do. You should multiply it by 1 minus cosine, but if I can't do it to both sides, I guess I'm just going to have to do that to once. You follow me?
I follow you.
So what is the numerator then?
Cosine squared beta.
Cosine squared beta, difference of squares pattern. Fight the temptation to distribute. It is not productive, and leave it factored out in the denominator. All right? You're on the right track. Now what? That's a beta. Yes. My bad. Now what?
Now
1 minus cosine beta is sine.
1 minus cosine. This is sine or this is sine? Top is sine or sine squared? Sine squared beta up top. Now you're cooking. Then what? Then look what you're trying to get to.
sine.
You.
Oh my gosh.
Sine, yeah, there you go. Sine doesn't mean anything to me, but yeah, if you divide out, then you have sine beta is 1 minus over 1 minus cosine beta is itself. You follow me? So if you can't multiply across, then do the next best thing. Multiply what you want to multiply by to just top and bottom. Yeah, what? Okay. All right. Here we go. Golly willikers. So this guy, we can use the left or the right side. We almost always work the left, but that's not a rule. You don't have to work the left. You can work whatever side you want. It's probably about the same amount of work either way. Do you have a preference this time?
Based on your language, I think we should work it out.
No, I don't. I think it's the same either way. Just give me something you can do. Okay, so none of those are known identities because there's no squares, yeah?
Yeah.
So what is cotangent by itself equal? Cotangent is equal to cosine over sine. Now, because that's the same replacement, you can absolutely replace both of the cotangents at the same time. That is not 2 steps, that is the same substitution. And that is allowed. Pretty cool. Now, it helps to, you absolutely can never cancel part of the sum. Think numerically. How about this? 3, no, I want to make sure you never do what you just said. Okay? Do you agree that this should be 4 over 2? Okay? But if you cancel those, is it 4 over 2? No, you just broke them. So you never cancel part of the sum. Never. Never. Okay? So multiply by a sign, you say. I love it. Let's multiply by, do I love it? Do I love it? Multiply by sine over sine?
Yeah, you just cancel sine. It's just cosine.
1 over sine plus 1 over cosine. Okay, so I think you're on the right track, but I think you're multiplying by the wrong thing. Think of where you want to go. Wouldn't you want to get to something like 1 over sine plus 1 over cosine? Isn't that what you want to get to in order to be here? So you would want to multiply by not cosine, but
1 over.
1 over cosine. Multiply by 1 over cosine.
But those cancel. It's top and bottom.
Now, when I say multiply, it's not just the first thing times 1 over cosine, it's the whole thing. You have to distribute.
But then the cosines just cancel.
Not only here, but not there, right? Okay,
Oh.
so when you multiply it there, what happens? And you get 1 over sine. And then when you multiply it there, you get 1 over cosine. These are betas. And in the denominator, again, you're distributing. So, 1 over sine minus 1 over cos.
Can we do that in one step, please?
Sine. Yeah, it's just distributing, so it's fine.
Oh, we distributed top and bottom.
Yeah, but it's the same thing. We're doing the same thing, so yeah, it's fine. Okay? Now, we're almost there. 2 steps. What now? What's 1 over sine equal to? Cosecants. Okay. Both of those are 1 over sine, so you can absolutely do both of those at the same time. The 1 over cosine we're going to have to do in the next step. Okay, again, that was the same substitution, so that is fine and dandy. And then, 1 over cosine and 1 over cosine both get replaced by secant. And then you say boom. No, you don't say boom. Because that's not something you say, I guess. Alright, so, are we cool so far? Alrighty then. So it's a lot of algebra so far, not new identities to remember. These are really just algebra-based identities. All right, what do you reckon we could do on this bad boy? The left side's way more complicated, so we'll want to work the left. There's always more to do on the complicated side. What do we do? Undistribute?
No, I don't think we do that.
Expand. I like expand. That's actually the vocabulary. Can you do that mentally, or do we need to write it? Yeah, I think I'm going to show it because I am worried we'll blow it. But
Why would you?
You have so much faith in us, too.
I don't. It's just
Why would you take it all out? Why would you do that?
because it's easier to. So I guarantee you, if you don't write it out, the first time this happens on a test, half of the people will say, "Oh, this is u squared sine squared plus v squared cosine squared," which is total mathematical. First, outer, inner, last. That is how you expand, and that's why you write it out, so you don't make that silly just square each one kind of mistake. So, when I distribute out the first one, FOIL it, first, outer, inner, last, what do I get? U squared sine squared. U times U is U squared. Sine times sine is sine squared. Then,
2u sine.
you're almost there, but you're wrong. Try again. U, V, sine, cosine. How many of them? 2. So 2, U, V,
Well, do we have to write out the entire
sine, cosine. No. I can definitely expect you, at this level of pre-calculus, you guys should be able to distribute
No,
and combine like terms at the same time.
but can we do that? Like, can I go step by step? Can we do it all in one line?
Yes, absolutely.
We can.
Yes, this is an algebra 1. Yeah, I mean, if you're an algebra 1,
No, but like for the identity.
this is algebra. This is not making substitutions many at a time.
Oh,
Okay, your whole purpose is to not lose somebody following you, and nobody's gonna be lost there. Where are we left at here? What else do we have? V squared cosine squared. That's the first one multiplied out. Are you with me so far? Okay, cool. How about the next one multiplied out?
Same thing, but a negative.
U squared cosine squared theta
Minus.
minus 2uv sine theta cosine theta. And minus or plus? Plus what? V squared sine squared theta. All right. Are we good at that point? All right. Now what do you see? That's all right. The sine squareds and the cosine squareds, and what about those sines and sine cosine mixture problems? These guys do subtract away. Identical, but one's negative, so they're goners. 2uv sine cosine minus 2uv sine cosine, they're goners. Now, what I think it was Aubrey that said sine squareds and cosine squares together. Do you agree that addition, we can switch the order whatever way we want, yeah? So I'm going to put these two guys together, and the reason is that they both have a u squared. It would be, I could see where you're coming from if you were saying, hey, put the cosine squareds together. Actually, you could do it either way, couldn't you? No. No, either way, it's going to be the same. Okay? Then what? What else do I have to put down? The v's, v squared cosine squared plus v squared sine squared. Cool. What can we do now? Factor out. What here can we factor out? U squared, leaving me with sine squared plus cosine squared. And what here can we factor out? V squared, leaving me with sine squared plus cosine squared. Those are both the same identity. What is that identity equal to? 1. So we get u squared plus v squared equals u squared plus v squared. You good? Alrighty, let's switch gears and talk triangle inequalities. Now, did you say oh? No. All right. First of all, a basic idea of triangles is kind of the T-Rex idea. If A and B are too small, like little smart arms, then what happens? They don't connect, and you don't get a triangle. Okay, so the first thing you should always talk about is I guess you could call it the T-Rex principle. And don't say that at college because that's not really a thing. But that is that, what, if the two sides have to be long enough to connect, what does that mean about A, B, and C and how they relate?
Triangle. And then you don't get triangle.
No, tell me how A, B, and C relate.
They equal each other. A squared.
They equal each other? They all equal each other?
No, but
No, sir.
it's the equal sign on the bottom.
Forget all that. You're not even looking there. Look at that picture.
A squared plus B squared has
No squares.
A plus B.
A plus B has to equal C?
It has to be big. C has to be bigger than A plus B.
Yeah.
C.
If A and B are equal to C, then that is not a triangle. Okay, so let's say it one more time. A plus B must be greater than C, or the two smallest sides added still must be greater than the third side. Even though they're small sides, they can't be so small that they don't even make a triangle. It's the, like I said, it's the T-Rex principle. Where did it go? Darn it! Oh well, maybe I'll
Let's see it.
see. See, don't you?
It's a T-Rex.
Yes, I get it. Thank you. Good commentary. Thank you. All right. So the next idea is what has to happen for certain types of triangles. If it's perfectly a squared b squared equals c squared right on the button, then it is a right triangle. Okay? Now, what I'd like you to say or look at this is now these aren't equal anymore, and if that happens because C got smaller. Now if C gets smaller, if C gets smaller, then what has to happen for the triangle? Acute, obtuse, or right if C gets smaller? Acute. Okay? If C gets smaller, it must be an acute triangle. What if C got bigger, so they're not inequality anymore? If C gets bigger, then it gets to be a bigger gap, and therefore obtuse. Now, that said, without any angle marks shown, you should be able to not state, but prove triangles are acute, obtuse, or right. No calculator, no protractor, just by how the sides relate. Always, always add the squares of the two smallest sides. The big side is alone. Okay, now in this case, it would be 5 squared and 12 squared on one side, and 13 squared on the other. This, we don't know yet if it's going to be equal, less than, or greater than. So leave that unnamed. 25 plus 144. How does it relate?
They are equal.
They are equal. Now, because they're equal, we conclude
It's a right triangle.
it's a right triangle. If 6 squared and 12 squared compares to 13 squared, now you won't always have a picture. In fact, you'll rarely have a picture. Instead, you look at the numbers, 36 and 144 as compared to 169. What is 36 plus 144?
Who is bigger?
What is the sum? 170, 180, 180. Now that means that the two smaller sides are bigger, or the C is smaller. If the C got smaller, then it is acute. Okay? Last but not least, does it matter which side I put? Can I put 15 and 6 on one side? No, that's ridiculous. It will always come out acute that way. You always put the two smaller sides together and the biggest side alone. We know that the left side is 180 because it's the same two sides we just had. What's 15 squared? 225. And therefore this is obtuse. Last question. Did you even look to see that they really are triangles? Did you?
Yeah, I totally did that.
They're all connected.
That's, who's to say that those pictures are at all real?
But they are. What?
Okay, my worry for you is this. If I give you sides like this, if I give you 4, 7, 11,
There's a hint in it.
if you just say, hey, 16 and 49 and that's 121, ooh, it's obtuse. Well, you just ate it. Because that is not actually even a triangle. Because if this is 11, where would the 4 and 7 have to be in order to connect? Right on top of it.
Oh gosh.
That is not a triangle. They have to add to more than the first side. More than. All right. Would you then give me do this on some kind of note sheet. Scratch paper, you have 5, 6, and A. The triangle is obtuse. Give me a range for A. Scratch paper, yes, and some scratch paper. A is the third side that you do not know, and it is entirely possible.
So is A the hypotenuse?
There is no hypotenuse, you have no idea if it's a right triangle.
Oh.
Hypotenuse is a right triangle word. These are not right triangles necessarily.
Did you just, what?
It requires you to use two ideas you just learned. I'll even say, I'll give you A is the longest side. I'll give you that. So it's not two cases, it's one. Okay? I'll tell you A is the longest side.
And then it could be literally
Those are the two things you should consider.
Oh.
Oh, wait, then it would go like, oh, the sister one. Oh, that makes sense. No, because it has to be greater than 11.
And it's less than less.
Oh, sorry, one neighbor.
Oh, yeah. I would know.
That's so
It should be the other way around.
It should be less than
Yeah.
11. Wait,
What are you doing? You're doing what? Really made up?
no, my dad.
Oh, really made up? You were switching. It doesn't make sense. They can't be more than 11 and less than 61. It's less than 11 to make a triangle. So it's not too big, but greater than 61. Okay.
I don't know what I did, but.
In order for, so A, can A be so big that 5 and 6 don't even touch?
Don't you worry.
No.
It's got to be small enough. It can't be too big, so it's got to be less than what? So 5 and 6. The principle is two sides added must be greater than the third side.
So it has to be 11.
It has to be less than 11. It cannot be 11 and 1.
It has
It
to be
wouldn't less than 11. Now what about an obtuse? That's the other thing. For it to be obtuse, what has to happen? Use your reach from the other.
It has to be bigger.
Use that.
So it has to be square. So it has
Use
to be
the square.
61.
A squared plus B squared. Get ready.
Square root of 61.
Alright.
Do I have to show you again?
No, you need to get in the back of the line because you will. Hi. That's not possible. Sorry. You cannot be greater than 11 and less than root 61. That's not possible. There is no number that's greater than 11 and less than root 61. That's not a thing. How can you be more than 11 but less than root 61?
So like, you know they have to be big.
Oh my god.
It's by itself. This whole thing, and then you do this, and then you just plug it in.
And then it has to be.
Now we're talking.
Squared plus B squared equals 1. It has to be greater than whatever
So when you get 11, you got the first one. How do you find?
So that's where the obtuse, it has to be, imagine if it was straight up Route 61. If it was straight up Route 61, it would be a right triangle, right?
Well, where do you get the 61 from?
A squared plus b squared compared to the longest side squared, yeah? Now this is the longest side and these are the shorter sides, right? That's where Route 61 comes from. Now in order for it to be obtuse, this side has to be bigger than that side. So you have to be bigger than the sum of the squares, but less than the sum of the numbers. Make that triangle work. Thank you.
I don't know. They're really tough.
Maybe eventually you'll be making a building once you need to incorporate different sized triangles into the architecture. You need to use this stuff.
Hey, hey, wait, what are your questions? Hey,
That Eric did tell me at all.
okay, it's okay if Eric helps you a lot.
Hey, as long as I didn't give you something.
By the way, this, any carpenter out there in the world knows this idea. I mean, if you want to check that your shelves you just built are square, they would use a 3, 4, 5 triangle. If this gap is not 5, then they know they need to, and then I know it's the right angle. They check square without any tool, just measurement. Okay?
Well, there is a tool called a square.
Yes, yes.
But it's triangle. It's a triangular shaped tool called a square.
Yes. All right, on you go, up, onward and upward. I think 6 and 7 represent the new ones, I'm not sure. Is that what they mean by stamp? Don't take a nap, take a nap after school. I don't wake up your nap and make you do math, so don't do nap. All right.
It's a fun game.
Okay. So you have these notes, right? You're not. Please can't drop this folder so it's a little scary.
Don't know how it happened.
All right. So here is 92, day 2. Here's 92, day 1. Here's 91, day 2. Do you make the notes for 92, or were they on the back of 91? I believe they were. I believe they were. If they're not, no, I have the notes right here. Yeah, you should have the notes right here, okay? If you don't, alright? Alright. 6 and 7, are those the newer ones?
Hmm.